Hi everyone! In today's video, we're tackling the other 5 core practicals in some exam style questions. So I did the first 5 core practicals in last week's video, and this week we're tackling the other 5 core practicals. So I've got some questions. They're very similar to the style questions you're going to see in your GCSE exam. Now, if you guys want to have a go at the questions before watching this video, don't forget you can download the question paper if you use the link in the description of this video. So let's get ourselves started. Now, this first question is going to be about Hooke's law, okay? And the first thing I need to do is the big 6 marker. I need to describe a method the student could use to investigate the relationship between the extension of a spring and the force applied. I may wish to include a diagram. As we know, when it says that I may wish to include a diagram, what it means is that I need to include a diagram. So I'm going to start by drawing my clamp stand. And then, that wasn't a very good clamp stand. Let's try more like this. Lovely. Okay, so I'm going to put on my clamp stand. I've got a spring. I'm going to draw masses and a mass hanger. I'm going to label all of this as well, because that is the way to definitely make sure that the examiner knows exactly what's going on here. And I'm going to draw a ruler. Something like that. And I'm going to draw the ruler attached to the clamp stand. So I've got a spring, I've got masses, I've got a ruler, and I'm going to label the clamp stand. So what I need to do is, because I'm measuring the extension, I need to say some way of measuring how much that spring stretches. Now, there's 2 ways of doing that. I can either say that I'm going to measure the initial length of the spring, the final length of the spring, and take the 2 away from each other, or I can say, like I've done in here, that I'm going to line the ruler up with the bottom of the spring with no masses. Then that means that when it extends, I can measure the extension straight off that ruler, okay? Then I'm going to add 100 grams of mass at a time. I'm going to record the extension in some sort of table. I am going to make sure that I don't exceed over about 800 grams here, okay? Because if I go above about 800 grams, then the chances are that if this is like a normal laboratory spring, then my spring is going to start overextending, okay? And I want to make sure that I'm measuring the force versus the extension when we're within our limit of proportionality. So I'm going to do not exceed 800 grams of mass. Right, okay. So I've dealt with the extension, but then I need to talk about the force, okay? Because what I'm doing is I'm adding masses. And how do I convert mass into force? I'm going to use the weight is equal to mass multiplied by gravitational field strength equation. That's how I'm going to work out how much force those masses are exerting to find the force, and then I'm going to draw a graph with force on the y-axis and extension on the x-axis. And that should be more than enough to get me 6 marks for this question. Now, for part B, I'm told that the student collects the following results, and I need to describe the relationship between force and extension. So to start with, as soon as I'm asked to describe a relationship, as one thing increases, what happens to the other thing? So as the force increases, the extension increases. Now, this is a 2-mark question, so that's not going to be enough to get me the 2nd mark. So for the 2nd mark, I need to make some sort of comment about the pattern. And if I look at my results, as I double, as if I go from 1 Newton to 2 newtons of force, the extension doubles. As I go from 2 to 4, in the force, the extension doubles again. So this means that my results are directly proportional. So that's going to be my second mark. So the results are directly proportional. And that's going to be how I get my second mark. Then for C, I'm asked to calculate the spring constant of the spring using the equation F is equal to KE. So I can actually just pick any pair of results that I want from the table because they're all within the limit of proportionality. So let's say that I pick the last one, but it doesn't matter which one you pick, you should always get the same spring constant. So F is equal to K multiplied by E. So the force is going to be 4 is equal to K multiplied by the extension, which is 8 centimeters. So I'm going to convert that to 0.08 meters. So the spring constant will be 4 divided by 0.08. I'm just going to grab my calculator here. 4 divided by 0.08 gives me an answer of 50. So the spring constant is 50 newtons per meter. You'd get both marks if you just wrote 50, not necessarily newtons per meter, because the question didn't ask you for the unit. Then, for part D, we're told that as the force continues to increase, it might not be possible to use F is equal to KE. Explain why. So this is because as the force increases, the limit of proportionality will be exceeded. So as we continue to increase the force, eventually we're going to get to the point where we're overstretching that spring. That as we add force to the spring, the extension isn't going to be increasing directly proportionally because springs can't extend forever. We know this. Eventually they break. So as F increases, the limit of proportionality will be exceeded. So the extension will no longer be directly proportional to the force. And there you go. That's how we're going to answer this first question. Question 2 is good old Newton's second law. Investigate how resultant force affects acceleration. Lovely. So the first thing I need to do is describe how the student can measure the acceleration of the trolley. So the equation I know for acceleration is A is equal to V minus U over T, right? Where V is my final velocity or my final speed, U is my initial velocity or my initial speed, and T is the time it takes to go between these two velocities, okay? Now, because my trolley can start from rest, I know that U, my initial velocity, is going to be 0, okay? So the next thing I need to work out is how I'm going to measure that final velocity. Now, the final velocity is the velocity of the trolley right at the end after it's done all of its acceleration. But actually, if I can work out the average velocity, the final velocity will just be twice of that because the average velocity is the velocity of the trolley in the middle, and at the end it's accelerated by the same amount again, so it will be twice the average velocity. So I can calculate average velocity using speed or velocity is distance over time. I need to measure the distance. About a meter is good with a ruler. And I'm going to measure the time with a stopwatch. And then the final velocity is just going to be twice the average velocity. And there you go. That is how I'm going to measure the acceleration in this question. Equally, you could describe a method using light gates. You could have talked about measuring the initial velocity with a light gate at the start, the final velocity with a light gate at the end, and timing how long it takes the trolley to move between the two. But don't forget, if you're going to talk about using light gates, you also need to include how you're going to use the data logger. So we never talk about just having a light gate, we always talk about a light gate and a data logger. Right. For part B, I'm actually given some numbers and I'm asked to work out the acceleration of the trolley. So I'm told the trolley reached a velocity of 2.5 meters per second. So that's going to be my final velocity. I'm told the trolley starts from rest. So my initial velocity is going to be 0. And the time between the two is 5. So that's going to give me 0.5 meters per second squared acceleration. Now, for part C, I'm asked to state in a variable that should be controlled in this investigation. Now, we know that Newton's second law is F is equal to m times A. So, resultant force affects acceleration, but mass also affects the acceleration. So, the thing that I'm going to control in this investigation is that the mass must remain constant. And then the final question asks me to explain how friction affects the results. So in perfect physics world, we have no friction. So the only resultant force, the only force acting on this trolley, so the resultant force is just going to be whatever I want it to be. Maybe I'm using masses that are dangling down off a pulley, for example, okay? But friction is actually going to reduce the size of the resultant force because friction always acts in the opposite way to motion. So we're going to say that friction will reduce the size. That's not how we spell size. We're going to try that again. The size of the resultant force. That's your first mark. Resultant force. So what will happen? The acceleration will be smaller. So if you look here, we've got F equals ma. If the resultant force is smaller, then the acceleration is also going to be smaller. So that's how we're going to answer a question on Newton's second law. Question 3 is about waves, and we're starting with a ripple tank. So remember, a ripple tank is when we use a vibration generator to create ripples in water, and we normally shine a light through them to get a shadow on the bottom, okay? So describe how a student can measure the wavelength of the waves. So what they need to do is they need to measure across 10 waves with a ruler and then divide this number by 10. We measure across 10 waves to increase our accuracy, okay? So if we measure across 10 waves, then what that means is that we're taking a larger measurement, then we're going to divide that number by 10 to find the length of one wave. Now, the student measures the wavelength to be 0.02 meters and the frequency is 10 hertz. We need to calculate the wave speed. So the equation I know for wave speed that's got frequency and wavelength in it is V is equal to F multiplied by lambda. V is my wave speed, F is my frequency, so that's going to be the number with hertz on the end of it, and the wavelength is measured in meters, so that's going to be 0.02. So therefore, my wave speed will be 10 times 0.02, so that's just going to be 0.2, because it's a speed, I measure it in meters per second. So your first mark would come from using the correct equation, your second mark would come from getting your substitution correct. Right, the student has now set up changed their practical, so they're now looking at the waves on a string. And we need to describe how the student can measure the wavelength of the waves on a string. So what we've got here is we've got what's sometimes called a standing wave. So you get these patterns when the wave is sent along the string and then it reflects. So the filled in line is the wave going along the string. The dotted line is the wave reflecting, okay? And these waves kind of join together to make this pattern. But what we need to do is we need to be able to measure a wavelength, okay? I think of these guys as being sausages. Now, we know that a wave needs an up and a down. So one wave, or one total wave, is 2 sausages. Okay, we're not going to talk about them in our exam as being sausages. Okay, but I think they look like sausages. We might call them loops. So we're going to say that they need to count the loops on the string, and then they need to do the number of loops divided by 2 to find the number of waves. Okay, so here there'll be 1, 2, 3, 4 loops. Divide it by 2, so that means that there are 2 waves. So we know what the distance is here. We're told the length of the string is 2 meters. So if there are 2 complete waves in 2 meters, we're then going to do the length of string divided by the number of waves, and that will give us the wavelength. So that's how you're going to do this for any practical setup that looks like this. Okay, question number 4 is triple only content. So you only need to be able to do this question if you're doing triple. That means you're doing a GCSE in physics itself. Okay, if you're doing combined science, you don't need to know this one. So we're investigating refraction of light through a glass, and we need to describe a method the student could use to measure the angle of incidence and the angle of refraction. So the first thing that we're going to do is place the glass block on paper and draw round it. That is mark number 1. Okay. We're then going to draw a normal at 90 degrees to the surface of the block. Don't forget to always add what angle we're drawing our normal at. Okay. We're going to shine light in to where the normal meets the block, and we're going to mark the light entering and exiting with pencil crosses. We are then going to take the light and block away and join up the crosses. So now we should have a diagram that looks a bit like that. And then we can simply use a protractor to measure the angle of incidence and refraction against the normal. Any 5 of those points will get you your mark here. Now, for part B, we need to explain why light changes direction when it enters the glass block. So light travels slower in glass than in air. So one part of, that's not how we spell V, the light wave hits the block first, slowing down first. So it's like if you drive a car into mud with one wheel but not the other, the car's going to spin because one wheel is now going slower than the other. And as part C, we need to state one source of error in this experiment. There are quite a few sources of error in the experiment. So we could have a defect on the surface of the block. The other thing that we could have is that the ray of light diverges, which means gets wider as it goes through, which will make it more difficult for me to measure. Other errors we could have had is that if we took multiple readings, we might not put the glass block back in the same place every single time. Infrared radiation is question 5. There are lots of ways they can ask this question. So this is just one of them. We've got 4 metal plates, they're heated to the same temperature and they're left to cool down. So part A asks us to work out which surface is going to be the best emitter of infrared radiation. It's going to be the matte black metal plate, because we know that matte black is the best absorber but also the best emitter of infrared radiation. Now, for part B, we need to describe how the student could carry out this investigation. So, the student needs to leave the plates to cool down for the same time, let's say 10 minutes. So, for 10 minutes. You need to say somewhere between about 5 to 20 minutes here, because we need to give some sort of example of how long we think we should leave these plates to cool down for, okay? 5 is be enough. 1 or 2 minutes, we're probably not get enough for a difference in temperature. 5 minutes, 10 minutes, something like that, we're probably going to get enough for difference. So leave the plates to cool down for 10 minutes. Measure the temperature of the plates after 10 minutes. We can use a thermometer for this, using a thermometer, and then we would need to calculate the change in temperature, assuming that we know what the starting temperature is. If not, that could be another marking point maybe, is that we could say that we would measure the starting temperature for leaving the plates to cool down. However, this is only a 3-mark question and we're told that the 4 metal plates are heated to the same temperature, so we should be okay. Now, the plate that's got the biggest change in temperature is going to be the one that is the best emitter of infrared radiation. Now, for the final part, I'm asked to suggest a control variable in this experiment. Now, most people would go straight in for the fact that the 4 metal plates need to be heated to the same temperature. Yeah, but we were told that in the question. So I'm going to go for the area of the plates needs to be the same. Because if we had a plate that had a bigger area, it's going to cool down quicker than a plate with a smaller area. So we want to make sure that the area of the plates is the same. And there you go. That's how you're going to answer these questions. I really hope you found this video useful. Don't forget that if you want to download the questions to have a go at yourself, to check out the link that's in the description of this video. I'll see you soon. Take care. Bye.